y when x takes certain value which is feasible. That is, if x is never realized under this probability distribution, what's the point of defining it? So really what we want to do is we want to understand what is the set of all x's that are realizable. Okay. Now, of course, that we would define, at least we will call that as a support. Okay. But because we have this structure, actually support has much nicer form. In particular, support of P of x is the following set of all x's such that a probability of a closed ball around point x of radius r is strictly positive for all r greater than 0. Look at set of all x's such that this is true. This is the support. That is, let's call this as Sx, then Px of Sx is 1. Okay. And this is this definition is instrumental. This will help us make all sorts of statements very clean, and that's why primarily the separability assumption. The Polish will come useful when we want to sort of argue more generally, and I'll make that clear in as we go through that. Okay. All right. So those are all the technical assumptions we'll consider throughout the talk. Okay. Nothing more, nothing less. Well, maybe one more. Okay, and yeah. So why couldn't be? Sorry? Yeah, that's correct. So all I'm going to say is that y takes value within a bounded interval. Now it could be discrete, that is, it could be 0 or 0, 1, or it could be any. It could be continuum. Okay. It's a time for algorithm. Actually, I have not defined the problem. Sorry. So now, first problem. Okay. Now, one way sort of we can again, we are interested in the following meta problem, right? Given x that you observe as features, you want to predict y. Okay, and there is nothing regression or classification about it. It's in a sense it's in our mind. Or putting it other way, regression and classification, thinking of continuous versus discrete, really that's realized through the metric or error metric that we define. So why don't we look at, so what we'll do is we'll define two error metric, and that effectively will translate into regression or classification. So the regression is the one, so goal is given x in, let's say, support of x, predict y so that you want to minimize some error. So one form of error is, let's suppose that your estimator is called, suppose your estimator is called f. Say f is a measurable function that takes x and maps it to r. In particular here, let's say the set y, say between y min and y max. What you want to do is you want to minimize expectation of y minus f of x square, given that x equals to x. And again, we all know this, that the minimizer of this is nothing but regression function or conditional expectation, which is expectation of y given x equals to x. And if you have not seen this, would be useful exercise, but I doubt if anybody has not seen it. Okay, so that means that we want to, if we go for minimizing squared error, then we want to go for conditional expectation. And so that means the goal is to find eta hat, let's say eta hat of x, such that eta hat of x is approximately equals to eta of x. In particular, if we suppose I have my estimator is eta hat, or say f, what is the error? Well, the error is nothing but expectation of y minus eta hat of x square given x equals to x, which is equal to y minus eta of x square given x equals to x plus eta of times y minus eta of x given x equals to x plus, given that x is given, it's eta of x minus eta of x squared, right? Now this is in a sense the minimal error possible. This, given that y eta of x is conditional expectation of this is 0, sorry, it's a squared error that matters. Or if okay with that, maybe what we want to really do is we want to minimize eta of x minus eta of x, and ideally for all x in support of x. So really, this would be our goal. That is, find eta hat of x such that eta hat of x and eta of x are close to each other for all x. Okay, so that's our this is our target or goal. Okay. I say, well, what happened to classification setting? Okay, what happened to classification setting? So actually, maybe good point. Maybe more precisely, I want to minimize where this is over. Yeah. Okay. Sorry. So I'm going to sort of focus on one norm just to keep things well contained. 2 is just simple. Thanks. Okay, because this will help me translate into the classification immediately, and I don't want to sort of go between 2. It's the same argument. All right. Anything else? All right. So let's. That's basically sort of used, for example, there. It's a simple but nice argument. Okay. That's correct. That's correct. But whatever argument I'll present will sort of take care of the square too. The one norm helps me reduce to classification simply. I thought I'll just focus on that. It's a representative argument instead of doing 2 things. Absolutely. Anything else? Yes? Yeah, well, this well-defined object, right? I mean, this goes back soon after Bourbaki's, I presume. Sorry, your question. No, bias and variance will show up. Yeah, we'll talk about it. Yeah, so it'll show up in the sort of my it will definitely sort of show up in if you're thinking of algorithms, it will show up in sort of how many things I take and so on. It'll show up. Okay. So right now, I haven't told you about algorithm. I haven't told you about observation. All I'm saying is that you have an estimator eta hat. I have an estimator eta. I don't know how you found it, but all I'm saying is that if you had an estimator, maybe I try to sort of see what happens here. Okay, so in some sense, you can say that, well, you had lots of data, whatever, however it was, you produce your eta hat. Now I want to use that eta hat on new unknown data that I have not seen before, but it's generated as per the underlying distribution, as per which potentially you saw the data and you learned your estimator, and I want to understand how well it's doing. But this new thing has nothing to do with your past, other than the fact that it's coming from same underlying distribution. Well, there are measures in some sense, right? I mean, because I'm actually, yeah. But here, Sanjay is right. That is, if I think of this as a function, then sort of this is the nearest neighbor or non-parametric view of learning just functions rather than anything else. Okay. All right. So now just one quick remark about classification, and we'll not discuss classification after this. So in the case of classification, what is the error? Well, you want to minimize the what do I call? I guess you want to get things. What do I call? Okay, mismatch error. Let's call it. That is, my metric is again, x is what I observe. F of x is my predictor, and I want to minimize p of y not equals to f of x given x equals to x. And again, this is kind of useless if my y is taking value continuously. So really, maybe we're thinking here in terms of y taking value discrete, and to keep things simple, I'm going to say it's binary. Okay. Now, again, sort of as we all know very well, the estimator that minimizes the misclassification error or this mismatch error is the Bayes estimator. In particular, say y hat of Bayes would say that equals to 1 if probability of y equals to 1 given x equals to x is greater than or equal to half, and I'm going to sort of break ties in favor of 1 here for equals to half and 0 otherwise. Okay, and the misclassification error induced by Bayes estimator is the Bayes error, and in a sense that's the best you can do. And the fact that means that sort of no matter what estimator you take, y not equals to f of x given x equals to x is always greater than or equal to, I mean, this is triviality, y hat of Bayes of x not equals to y. Okay, and this averaged over, or after taking expectation of this with respect to x, is what I would call Bayes error. Again, I want to minimize that. So I want to sort of find an estimator so that it's as good as that. Okay, now, so far so good. So the question is that, first of all, what does this have to do with eta? Well, in this case, it's really nice and simple, right? Because what is my eta of x? Eta of x by definition is conditional expectation of y given x equals to x, which is equal to probability of y equals to 1 given x equals to x in this case. That means that my Bayes classifier can be rewritten as indicator of eta x greater than or equal to half. Okay, so that means that so what I really want to do is I want to estimate, now I want to estimate eta hat such that, not really minimizing something like this, right? Potentially, what we really want is I want to minimize, I want to find eta hat so that this decision is correct most of the time, or rather all of the time ideally. Okay, so even if let's say eta x is 0.75 and I estimated my eta hat to be 0.51, that's fine. So large error, but that's fine. On the other hand, my eta x is 0.50111 and I estimated 0.49999, that's bad actually. Okay, so putting it other way, if you want to, so let's say draw a picture So if you want to draw a picture of, let me try to use space efficiently. Draw a picture of, let's say this is the value between 1 and 0, and suppose this is representing x. Let's say this is half, and let's say this is the place. So suppose original eta, and again I'm just drawing this, is like this. This is the underlying eta. And let's suppose I've got this really, really good estimator almost all the places, and then it jumps like this, goes like this, like this. This is worse than this kind of an estimator, right? So really sort of what matters is, as people call it, is a boundary or this margin. And the question is that how do we sort of get this right? Okay. Now here's so I mean, you can obsess about margin if you like. Maybe all of your mass of x is such that sort of, let's say, px sort of entirely concentrates here. And then you can keep obsessing about it. But really, what is the interest? The interest is that I want to get my error, my estimator error close to base error, right? So then sort of what we can do is that suppose I had a method for estimating my regression function. Again, regression function eta now is actually takes value between 0 and 1, and x is my input. Effectively, this has become my likelihood, or likelihood has become my target. So if I knew how to estimate that well, in particular, if I had a way to find eta hat such that eta hat of x minus eta of x is less than or equal to epsilon for all x in Sx with a large enough probability. Okay, so let's suppose for the purpose of thinking of reduction, let's say this is true. So I found an eta hat of x which is close to eta x for all x. Then what I could do is I would define something like this. Let's say, let me define set of all things which are far, where I was thinking of x's that are away from this equals to half boundary by epsilon equals to all x in support of x such that eta of x minus half is greater than epsilon. Okay. So then over this set x, so for x in x far of epsilon, clearly this is equal to okay? Everybody's okay with that? Because look, over this set, this is greater than half only if it's half plus epsilon. And this must be, because it's close to eta by epsilon, it has to be at least half plus epsilon minus epsilon, which is half. And similarly, if it's less than half, then it must be half minus epsilon, because it's far from the boundary and same. So that means that over this set, my classifier coming from here, the plug-in classifier coming from here is same as the base classifier. So that means that over this set, my base error, misclassification error is same as my error. Okay. Now, when it's not, let's say, if x is in complement of this, what will be my base error? Well, let's suppose that sort of the Bayesian classifier said 1 and I said 0. How far can my error be from that? 2 epsilon, because I'm just around the corner. I mean, say we are here. So that is, given x, you will say 1, but well, you will be 1 with half, at most half plus epsilon. And I'm going to say 0, I'm going to be 0 with half minus epsilon. That means that y, true label not being me, is at most worse by base classifier's error by epsilon or 2 epsilon here. So that means that in this case, let's call it my error. Okay, pardon my poor definition here, is less than or equal to base error plus 2 epsilon. Okay. So which means that if I had a good estimator here, then I will conclude that my error more generally is no more than the base error plus 2 epsilon. Okay. And then the question is that, okay, that sounds great. Will this be true always? Well, maybe this may not be true always, but it'll be true with 1 minus delta. That's fine. When I make an error there, there'll be add sort of another delta maybe. Okay, but then sort of what's delta among friends? So then that'll be that. Okay, so the point is that if we get this right with high probability, then we will conclude that the classification error or misclassification error of the plugin estimator is no more than the base error plus small. Yeah. Well, I would like to, but I don't know. I mean, well, okay, so good. So, I mean, I think sort of, in a sense, okay, good. So I want to do base estimate. Okay, so to compute base estimator, I need to know the entire model. And the thing I have not sort of yet gone to, so I've sort of defined the setup, I've defined the problem, I've not told you the observation and algorithms. So, so far all I'm saying is that, look, what I want to do is that's my setup, that's my question. If I want to predict y to minimize squared error, this is my, actually the squared minimization is my goal, of course, or minimizing the square of this is my goal. But then I say, well, you know, grant me sort of a little bit of slack here, because the way we'll prove this will be the same way we can prove the square too. So with that in mind, let's say we want to minimize this quantity. If you minimize this quantity, that's the right thing to do, and that's what a regression algorithm would like to do. A classification algorithm would like to, what it would like to do is, I'm trying to argue, is that the same thing, effectively. Okay. So okay. So now sort of, so if I have a hat that is good in this form, let's say that's less than or equal to epsilon, I've effectively solved regression and classification problem. So then that means that sort of my revised target is, for a given setting, go find eta hat such that it's close to that. Now, in the process, if you can get eta exactly, excellent. If you can't, try to minimize that. Okay, and now sort of it's a perfect setup. So the question is that, okay, so how do we do this? All right, so now I'm not going to talk about classification, and I'm going to just continue focusing on this, or these two. So how do we do this? Okay, so now I need to define observation. That is, what do I observe really? Okay, so observations are, as you would expect, I've got a bunch of samples of xi, yi coming from this joint distribution, the way we have set it up. And let's say the number of samples I'll represent is n. Okay, so these are the samples. And I want an algorithm. An algorithm is, pretty sure there's a right way to put the pressure on the chalk that it doesn't break. Algorithm is, let's call it, first I'm going to talk about the k nearest neighbor algorithm. Think of k some integer greater than or equal to 1. So again, setup is that I am observing some x in my support, and I want to find out, predict y. How am I going to do that? I'm going to look at all my data points. I'm going to order them with respect to x. That is, suppose that these are reordered such that, and hence I'm going to use this index, xi of x, and corresponding label are yi of x, where, okay, whereby this reindicing, I mean that x1 of x is the point in this that is closest to x with respect to metric row. That is, putting it other way, row x of x1 of x is less than or equal to rho x x2 of x. You mean closest point? Yeah, and hence inequality. Perfect. Yes, so you will have ties and all that stuff. Perfect. Okay, especially if you have features which are discrete, you are likely to see that. Okay, so you got this, and now you're going to produce your estimate of eta hat k nearest neighbor for x equals to 1 over k summation I equals to 1 to up to k y I of x. That is, look at inwards, look at all the data points that are out there and find the k closest data point to you, and the closest is defined as look at the x that you are observing, look at the features of the data points that you have seen, find out the closest with respect to the metric that you have in that feature space, and then look at their labels and then just average them. Okay, so that's the k nearest neighbor. It's a simple vanilla algorithm, nothing more than that. Questions? Yeah. Well, by definition, see, this may not lie in label space y. That's exactly right. But it will lie in the interval. Okay, good. Excellent. Anything else? No. So really, in discrete case, see, that's why sort of we sort of completely decoupled the whole graph. All I'm interested in eta hat, and eta hat is between 0 and 1. In that case. Of course. So I've got data points and data points, the x1, y1, x2, y2, x and yn. Okay. Now you got a new feature, small x, with respect to which you want to estimate its label. What I'm going to do is I'm going to take this x, and this x1, x2, xn. I'm going to go and find the point, the tuple in which corresponding x coordinate is closest to my x. Okay. Let me call that x1 of x. Okay. So it may be that